halogenation of an alkene in water. So, very similar to the halogenation of an alkene in an inert solvent, but an inert solvent means not reactive. If we have water as a solvent, water we know can be nucleophilic. It can also, in some circumstances, act as an acid or as a base. In this reaction, it is going to serve as a competing nucleophile. And the halogen for the reaction is going to be either bromine or chlorine. So this X2 is either molecular bromine, Br2, or molecular chlorine, Cl2. So the first step in this mechanism is the exact same as for the halogenation in an inert solvent. So we have the pi bond, which is a nucleophile, and we'll use bromine for the halogen. So the pi bond is the nucleophile, and it will attack the bromine, one of these two bromines, and break the other bond. And at the same time as this attacks, we have a positive charge building up here. We're taking electrons away from that carbon, and the electrons that are still on the bromine can come in and bridge that positive charge. So we get a cyclic brominium ion intermediate, the exact same intermediate that we saw in the halogenation in an inert solvent. So here is the cyclic brominium ion intermediate. So this brominium ion is a high energy intermediate, and it will react with any nucleophile that it finds. So it is a high energy intermediate, will react with any nucleophile. So in this solution, we need to think about the nucleophiles that we have. We have some bromide ion that was liberated here, and then the reaction is being done in water. So if water is the solvent, it means that everything is surrounded in water. We have a lot more water than we do anything else in this solution. So it's very likely that the water is going to be the nucleophile that ends up attacking this brominium ion, simply because we have so much more of it. So if the water attacks, it's going to attack one of these two carbon atoms, and it's going to break open that cyclic brominium ion. This is still an anti-addition, right? We see the alcohol is going back into the plane. The halogen is sticking out of the plane, and that's because of this attack right here. This is where your anti-addition occurs. Okay, so the addition is anti, right? And that's because the brominium ion is sitting up, and then this nucleophile is going to attack from behind the plane of the paper. So we will see the brominium ion sticking up. We've broken this bond. We still have a bromine here sticking out of the plane of the page. So there it is. And then the water has attacked from behind the plane of the page. So we put that on a dash bond. And this is what we have initially. So this looks very close to the product, which has an alcohol and a halogen. So that's why it's called a halohydrin. We just need one proton transfer step to get to there. Water, again, we have a lot of it. It's the solvent, it's surrounding everything. Water will be the base that is going to pull off one of these hydrogens. So I'm going to use another water molecule. It will remove one of these hydrogens, and then these electrons will go to the oxygen in order to neutralize that positive charge, which gives us the halohydrin product.